Hello and welcome. So, in the last module we were looking at the optical fiber. We started off with a single mode fiber and we said very briefly a simplistic picture based on the geometric optics why total internal reflection is required for the wave to propagate inside the core. The objective of the optical fiber is to cause the mode to propagate inside the fiber, and that is possible when you shine light on the fiber and you get the light into the core. The core cladding interface must allow a total internal reflection, because once there is a total internal reflection in the core cladding interface, whatever the power that is going from the core will be reflected back into the core itself. Of course, for all angles it will not happen, it will happen only at specific, only after a specific angle is reached. So, as you start increasing the angle phi of the incidence at the core cladding interface, you have to reach a certain angle called as critical angle, which is a function of n1 and n2 in order to basically induce the total internal reflection. Once your angle of incidence is larger than phi c, then at those angle the ray will be reflected back. Which angle will the ray be reflected back? This is something that sometimes students get confused. Well, if you take simple interface of refractive index n1 here and n2 which is less than n1, and let us say you send in light at an angle of phi. Okay. Now, even without the total internal reflection, there is always a reflection happening at the same angle phi. This is the simple reflection because of the interface between two media. When total internal reflection happens, the reflected ray will be at the same angle phi which was the transmitted angle. This is of course the first Snell's law. So, when the angle of incidence is phi, the angle of reflection will also be phi. For any angle which is greater than the critical angle, assuming that we are at a critical angle for the red curve. So, for any angle which is greater than the critical angle, right, your total internal reflection works, and therefore, all the light will be guided in the core. Okay. Let us see what restriction does this critical angle place on the incident angle theta I. I mean, after all, we are taking light from a laser source or some other source and then coupling the light from this one. So, this is basically a lens source which I am using it to couple light from, for example, this could be a laser source. Okay. So, this would be the mode coming in from the laser, and this has to be coupled and focused onto the core. What should be the cone of this cone angle of this one? What is the maximum cone within which the light coming from the light source will be accepted and guided by the core is called as the acceptance angle, or sometimes called as the numerical aperture. Okay. So, let us derive an expression for this numerical aperture by writing three laws. One Snell's law at the interface of air, which is where we are coming in with the light from and going into the core region. So, air core interface will give you one equation which is sin theta I is equal to n1 sin theta 2, where theta 2 is this angle which the ray of light, the red one, is refracting from the incident blue one. So, this angle is theta 2. Okay. However, I can relate theta 2 to phi, because theta 2 is not required for me to calculate the critical angle at the core cladding interface. What I need is phi, and I know that theta 2 and phi can be related, because if I complete this right angle triangle, then I know that phi is given by 90 minus theta 2. So, or theta 2 is given by 90 minus phi. I can use this expression for theta 2 into this one. I know that sin of 90 minus any angle phi is cos phi. So, in place of n1 sin theta 2, I can write the right hand side as n1 cos phi. So, the left hand side is sin theta. You might ask, what happened to the refractive index of air? Well, refractive index of air is just equal to 1, therefore, I did not show that explicitly. Okay. So, we have come up to this one, we have applied the interface at the air and the core interface. So, this is basically air core interface equation. Now, you have another equation at the core cladding interface, right. So, this is the equation at the core cladding interface, and this equation where we have written phi c implies that you are looking at the critical angle of the core cladding interface, and critical angle of the core cladding interface is given by sin phi c. Solving this particular equation, sin phi c is equal to n2 by n1. Remember, n2 is less than n1, and therefore, critical angle is any value between in the first quadrant 0 to pi by 2. So, let us say this is the critical angle, and we hope and expect that all angles of incidence phi which lie between phi c and pi by 2 will be guided by the fiber. Okay. So, this is n1 sin phi c equal to n2 will happen at the critical angle for the core cladding interface. Any angle phi greater than phi c will also tell me that if I go to the same core clad interface equation, that n1 square sin square phi, phi being the angle of incidence, which is which we have shown here in this picture. So, this is the angle of incidence. So, when phi is greater than phi c, then n1 square sin square phi is greater than n2 square. Obviously, for this reason you do not get the real solution for phi, and hence you get the total internal reflection. But other than that, this equation is valid for phi greater than phi c. So, once your angle of incidence becomes greater than the critical angle, then n1 square sin square phi will be greater than n2 square, because sine of the refracted way here would anyway become equal to pi by 2. So, this would have been gone, but I can relate sin square phi to cos square phi, because sin square phi is nothing but 1 minus cos square phi. So, n1 square into 1 minus cos square phi must be greater than n2 square for phi greater than phi c, and just rearranging this, open up this bracket and then pull n2 square to the left, and then you will realize that this equation is equivalent of n1 cos phi being less than square root of n1 square minus n2 square. Okay. But I know what is n1 cos phi. N1 cos phi is nothing but sin theta I. Therefore, what I get is sin theta I is less than n1 square minus n2 square under root. Now, we have two possibilities. One, if n1 square minus n2 square is much larger than 1, then any angle theta I is possible, right. Sin theta I, if this value is greater than 1, then any angle, this square root fellow is greater than 1, then any angle theta I will be accepted by the fiber. However, in practice this is not what happens. In practice, as I said, the difference between n1 and n2 for a single mode fiber is about 0.4%. It will change up to 1.5% for non-zero dispersion shifted fiber, and it will be around 0.6 to 0.8% for a zero dispersion shifted fiber. However, for single mode fiber this is very small, and even for any other fiber that is in the current fiber family, the difference, the refractive index difference n1 square minus n2 square is so small, in fact it is much less than 1. In that case, what happens as you start increasing theta I, so you look at this equation, as you start increasing theta I, sin theta I keeps on increasing, n1 is fixed. What will happen to n2? n2 should basically start to increase, which means that phi starts to decrease, and eventually if theta I reaches to its theta I max, theta 2 would have decreased in such a way that, theta 2 would have increased in such a way that phi would have decreased below the critical angle, and that particular ray would not be transmitted. So, if you were to send in light ray here, okay, so send in light ray here, then this would hit the core cladding interface at an angle which is less than the critical angle, and then this light would simply escape out. So, if this angle theta I is greater than theta I max. So, what is this theta I max? This theta I max is this cone angle. What is the maximum value of theta I within which the incident light is actually accepted by the fiber and it is propagated. Okay. So, that is theta I max, and this theta I max we will reach when sin theta I will be equal to square root of n1 square minus n2 square. Okay. So, this angle which you can obtain after solving this particular equation, sin theta I max is equal to square root of n1 square minus n2 square, twice of that angle 2 theta I max is given as, is called as the numerical aperture in some literature. In some other literature, theta I max itself denotes the numerical aperture. Okay. So, in some literature this is 2 times theta I max, in some literature this is just theta I max. You have to just look at it how the authors are defining and be clear about one of those. Okay. So, we will assume that theta I max is equal to numerical aperture and call this 2 theta I max as the acceptance cone angle. Okay. So, just to give you the kind of a cone idea, we will call this as the acceptance cone angle, whereas theta I max we will call as the numerical aperture. Because n1 is very close to n2, the difference between them is very small, this n1 square minus n2 square under root can be written as n1 minus n2 into n1 plus n2, and since n1 is very close to n2, we will call this as equal to n1. So, you will get here as 2n1 and this becomes 2n1, and then we can call this n1 minus n2, we will call something here, one second. So, this is n1 minus n2 under root. So, I can pull this n1 out, okay. So, I have theta I max is equal to this fellow. So, I can pull 2n1 out under root here, and if I define n1 minus n2 by n1 as delta, okay, which is the relative refractive index difference, then what will happen is n1 plus n2 is approximately 2n1 and n1 minus n2 divided by n1 is delta. Therefore, n1 minus n2 is equal to n1 times delta, okay. This delta is the index difference. So, this becomes 2n1 n1 delta, n1 is a n1 into n1 is n1 square, therefore, n1 can come out of the root and what you get is n1 into 2 delta. So, this is approximately the numerical aperture of the fiber. The numerical aperture of the fiber is roughly n1 into square root of 2 delta. Of course, this approximation you do not have to follow, because this is the exact expression for the step index single mode fiber. This is the exact expression for the numerical aperture. Calculate theta I max from this equation from your calculator. Once you have calculated, that would be the numerical aperture. There is no need to really do the approximation. This approximation is kind of a handy way for people to just put some quick numbers, but other than that you can actually use the real value of n1 square minus n2 square. And this is just a definition of the index difference. This is definition of the index difference with relative to n1. You can define just n1 minus n2 as delta, and then you will get a slightly different result here. So, you will get square root of 2 n1 into delta. It all depends on how you define, okay. So, let us do a quick example here to give you an idea of the numbers. Let us assume that we are looking at the core refractive index of 1.47 and the cladding refractive index of 1.45. So, the core cladding difference will be 1.47 minus 1.45 divided by 1.47. This is the value of the index difference delta, correct. So, this is your index difference delta. You can calculate this, what would be the value for that one, and then from here you can calculate what should be the numerical aperture. The numerical aperture is given by 1.47 times square root of 2 into this delta, right, which is 1.47 minus 1.45 divided by 1.47, and it turns out that this numerical aperture is approximately 0.2417. But remember, numerical aperture is nothing but theta I of max, and this is expressed in radians, okay. So, you want to convert this 0.2417 into degrees. If you want to do that one, then you need to multiply this one by 180 and divide the whole thing by pi. So, roughly pi is 3, so 3 and 60, 60 into 0.25. So, 60 by 4, this is roughly 15 degrees. Of course, the actual answer will be slightly different. You can calculate that one from your calculator, okay. So, numerical aperture, we have obtained the maximum angle of incidence theta I max. So, we had defined the numerical aperture as theta I max. We will define not theta I max as the numerical aperture, but rather sin theta I max as the numerical aperture. So, if we do that one, then what happens is that this is sin theta I max, sorry. So, this is sin theta I max. A small correction, we are not defining theta I max as the numerical aperture, but rather sin theta I max as the numerical aperture. So, sin theta I max will be n1 square root 2 delta, and you can, so this has to be slightly changed now. So, this is NA. Numerical aperture is still 0.2417, but the acceptance angle is basically sin theta I max, which should be equal to the numerical aperture 0.2417. From here you can find out what is theta I max. This is sin inverse of numerical aperture, which is sin inverse of 0.2417, and this is roughly 0.2441 radians. Of course, you can convert this radian into degrees, and when you do that by multiplying it by 180 and dividing it by pi, what you get is roughly 15 degrees. Okay. The refractive index difference delta can be calculated very easily, as you have already seen this one. Alright, so this was a simple example to show you what is the acceptance angle. So the acceptance angle is roughly 15 degrees onto this side and another 15 degrees onto that side. So if you were to find a lens, then this lens has to have a cone angle. Okay, if you want to put everything into this particular core, then the angle of this one should be, the cone angle should be 30 degrees nearly. Okay. So this calculation is useful when you are coupling light from a laser onto the optical fiber. So you have typically laser diode which would be emitting light from this side with a small non-zero divergence. Then you put a lens here in order to make it convergent, and then put this one through the fiber. Okay. So this is your fiber core and this would be somewhere here cladding. So this is how you couple light from a laser onto the fiber. Okay. So these calculations are required in order to find the lens power and the lens focal length of the lens. Okay. We will look at what is called as a multimode fiber. We have told you that multimode fiber means that it is possible to transmit more than one mode at the same time. In fact, what happens is that in a multimode fiber, when you excite the fiber with, or when you couple light into the multimode fiber, you will see that the fundamental mode or the dominant mode, which will begin to propagate right at critical angle, will be excited all the time. Thereafter, all the angles within which would not be excited, but rather only certain selected angles will be excited. Okay. So let us go back to the core cladding interface here. So this is the clad and this is the core, and let us say this is where my core cladding interface looks like, and light is coming in here at an angle of say phi 1. Suppose one more ray comes in here at an angle of phi 2, and we assume that phi 2 is greater than phi 1, and both these angles are greater than the critical angle. Therefore, both rays should get reflected. So this gets reflected here, the second one also gets reflected. Okay. So both are getting reflected at the same angles phi 1 and phi 2. Maybe this figure does not really show you that, and once again they will be reflected and they would be propagated this way. Similarly, this ray would also be reflected again and then it would be propagated, and then this is how this both modes will be propagating. Okay. So this is what happens in a multimode fiber, and this multimode fiber typically has a larger core radius. This is around 50 micron core radius. Okay. And the cladding is still fixed at 125 micron. So you can now see that the core region is quite large and cladding to core radius is just about 2 times, whereas for a single mode fiber, this cladding to core ratios, the diameter ratios or the radius ratios were about 5. Now one aspect that becomes very important when you are looking at multimode fibers is what is called as modal dispersion. Okay. So this modal dispersion simply means this. Suppose I take a pulse of light. Okay. So I take a pulse of light and then I launch this light into the fiber. Let us say both modes get excited, that is light energy goes into both these modes, and then these modes will propagate along the fiber. You can clearly see that these modes are propagating along the fiber at very different velocities, and then when they arrive at the receiver, when you put them back together, you will see that the pulse has kind of expanded. Okay. Okay. So earlier, if you now what happens is that if you were to send your pulses at a certain rate, okay. So let us say this is a pulses which are being sent, and each pulse carries an information, and let us say the time or of between the pulses is Tb, which would be equal to 1 by b, where b is the bit rate of the system. Okay. So you are sending out one bit represented by one pulse here. So you are sending out each pulse at a rate of 1 by b pulses per second, and then because of dispersion, each of these pulses there will be reduction in the amplitude, but more importantly each of these pulses would then be spread out. Okay. And then there would be one more pulse which is on that side spreading out a little bit like this. So it is spreading out in this region, you know, the actual pulse shape will change. this is in fact slightly better channel. Okay, if you were to wait for a longer time, what would happen is this fellow would be so wide enough that it will start occupying the neighboring slots, and therefore you will not be able to send pulses at whatever the rate that you want to send because of this broadening mechanism. And this broadening mechanism happens because of what is called as the modal dispersion. Sometimes it is called as intermodal dispersion. It is dispersion between two different modes of the propagation inside a multimode fiber. Let us try and get a very quick estimate for this modal dispersion parameter. Let us go back to the multimode fiber structure and then draw two extreme cases. One case is when I have a mode which is right at the critical angle, incident at the critical angle, and one where I have a mode which is incident almost horizontally. Okay. So, this is when phi is equal to pi by 2, and this will horizontally incident ray of light will actually transmit. Okay. I mean it will go back. The one that is incident at phi equal to phi c, if it has to reach the same point. So, let us call this point as point A, okay, and this ray gets reflected of course at the same angle. So, we have already assumed that this angle phi is just equal to phi c. So, this comes back to, so this point let us call this as C, and then this again gets reflected here, let us call this as B. Now, if I look at what is the time difference for the ray of light to reach a distance A to B, when you are incident this one at an angle phi equal to phi c, and when you have incident this one almost parallel to the interface. Remember, this was called as the grazing angle of incidence. Okay. So, because of the symmetry here, the total time AB can be written as the time taken by the ray to travel from AC and to CB, right. So, this would be the total time that is taken. So, if you call this as TAB as the time taken from A to B, this would be equal to the distance AB divided by the velocity with which this ray has been traveling. Okay. V1 is given by C by N1. Now, here is a catch. The distance AB is the longitudinal distance. It is not actually the distance which is the transverse distance that you have to consider. What I mean by this is that if you look at this ray, for example, what is this distance that you have to consider, the longitudinal distance that you have to consider? If this angle is phi, this angle is also phi, this length is say AC. Okay. So, you have AC cos phi and AC sin phi, right. So, you have AC sin phi, so AC cos phi and AC sin phi, therefore, this is AC sin phi. Similarly, this is BC sin phi, right, and AC is actually equal to BC in our case. So, we have the total thing to be about 2 times AC sin phi. Okay. So, you have 2 times AC sin phi, and if you assume that this is one section of the fiber, and then you can think of the fiber as having many such sections, and if you want to propagate over a length L, then you would have to propagate by so many sections. So, let us say n sections propagating or n sections of the fiber that we are taking. After n sections you are going to get the total distance of L, okay, and time taken for each section will be TAB. Therefore, the total time taken here will actually get multiplied by the number of sections, and this becomes n into TAB, right. So, what is TAB here now for the overall time length? If you call this as the length of propagation time TL, this is given by number of sections n, the length with which this as one section is traversed, which is the distance AB, and what is the velocity with which it has traversed? It is actually C by N1, right, that is the velocity V1. So, it is divided by V1. So, V1 is C by, sorry, this is actually N1 by C, this has to be N1. Here it has, in the denominator it has to be C, and in the numerator it has to be N1, and then it is not exactly AB, right. So, you have the total distance as AC sin phi, BC sin phi, AC is equal to BC, therefore, this is actually sin phi, right. So, this length which and since we have taken this 2 times sin phi as one unit section, so for length L there will be total of 2L sin phi things. So, since 2 is one unit cell for me, this would still simply be equal to sin phi. Okay. So, the distance AB is given by AC sin phi plus BC sin phi. By symmetry, this is actually equal to 2 AC sin phi, and this would be the distance that you are looking at. So, this would be the unit cell distance that you are looking at. So, the time travelled to traverse a fiber of length L is given by this particular expression, and since you are looking at n sections of AB, n sections of AB is nothing but L, right. Each section is of length AB. So, n times AB is nothing but L. So, you have time taken for any wave, any ray which is incident is given by L n1 by C into sin phi. Now, this is interesting. You start with the case when phi is equal to phi C, which means you are at the maximum value for light to propagate. So, this is what you get TL max, and this is given by L n1 by C sin phi C, but I know that n1 sin phi C is equal to n2, therefore, sin phi C is given by n2 by n1. So, I can substitute for that. So, I get L n1 by C into sin phi C is nothing but n2 by n1, correct. So, this would be n1 goes to the numerator, so it becomes n1 square L by n2 into C. When will you get the minimum length? So, minimum length will happen when phi is equal to pi by 2, at which point sin phi will be equal to simply pi by 2. So, you get minimum propagation time as n1 L by C. Okay. So, this is the minimum length, and the pulse essentially, if you were to assume that all the angles, or at least the angle at phi equal to pi by 2 and phi equal to phi C are excited, then the duration with which the pulse gets stretched will be equal to TL max minus TL min, and I will leave this as an exercise to you to show that this is nothing but n1 L by C into n1 by n2 minus 1, which is approximately n1 square L delta divided by C into n2. Okay. So, this length of delta t is given by n1 square L delta by C into n2, and this is the length over which your pulse actually gets broadened. Okay. For avoiding this dispersion problem, the pulse broadening problem which limits your bit rate, if you want to avoid that, this delta t has to be less than TB, right. So, this has to be less than or equal to TB in order to avoid one pulse crossing over to the other pulse. So, you can substitute for TB as 1 by B and replace this and multiply that one by L and rearrange the equation so that you get BL is less than or equal to Cn2 by n1 square into delta. This product on the left hand side is called as the BL product. It tells you the bit rate into length product, tells you that if you want a larger bit rate you have to reduce the length L, if you want a larger length then you want to reduce the bit rate. And for a given multimode fiber with the parameters n2, n1 and delta known to you, this would be the limit on the bit rate into distance factor. Thank you very much.